So now we're continuing our quest to figure out what is the volume of a cone. Where does that 1/3 term come from in 1/3 pi r squared times the height? And the way that we were trying to solve this was by looking at the volume of a frustum of a cone. The frustum being this part on the bottom that results from chopping off the tip of a cone. The tip, we said, has a height of h. The frustum is going to have a height of f. The area of the tiny cone that gets cut off, also the area at the top of the frustum, is lowercase a. Area of the base of the frustum is capital A. And we concluded that volume of the frustum should be the volume of the big cone, this whole thing, minus the volume of the small cone, this thing on the tip, which we said was equivalent to some constant that we don't know, times the area of the base, times the height of the big cone, minus a constant times the area of the little part, times the height of the little cone. Through a whole bunch of substitutions and shenanigans that you see in part 1, we came up with this as the formula for the volume of a frustum. The constant that we don't know times the height of the frustum times this term. The area of the lower base plus the area of the upper base plus the square root of the product of those two areas. Cool. We have a formula for the volume of a frustum. We still don't know what this constant is. So how does this help us? Well, consider this. If we have a frustum, this sort of volcano-looking thing, what happens to that frustum as the area of the top base gets closer and closer to the area of the bottom base, until finally those two areas are equal? Well, if these two areas are equal, then the frustum becomes a cylinder. One of the things about mathematical formulas is that they should be universal. Just because this is the formula for the volume of a frustum doesn't mean it shouldn't be able to work on this frustum where the areas happen to be the same size. A frustum with equally sized bases is a cylinder. And anything that should work for a cylinder should work for a frustum with equally sized bases. If that's a little confusing, consider this. In 2 dimensions, if we have a trapezoid, we say that the area of the trapezoid is 1/2 base 1 plus base 2 times the height. Well, what if base 1 and base 2 are equal? If base 1 and base 2 are the same size, we end up with something that looks like a rectangle, because it is a rectangle. The area is still 1/2 base 1 plus base 2 times the height. But if the bases are equal, that lets us write it as 1/2 base 1 plus base 1 times the height, which is 1/2 2 base 1s times the height, which is just base 1 times the height, which makes sense. This is a rectangle. Its area should be equivalent to the formula for a rectangle. So the way that a trapezoid with equal bases should have its area be the same as that of a rectangle, a frustum with equally sized bases should have the same volume as a cylinder. Well, I know area of a cylinder is area of the base times the height. Sorry, this should be volume of a cylinder. I know the volume of a frustum is some constant that we're trying to solve for, times the height of the frustum, times A, plus square root of A plus little a. Now we are assuming that the height of this frustum/cylinder is going to be F. The height of the frustum is the same as the height of the cylinder. And we know that the bases are going to be equal. This means that the volume should be equivalent to the area of the base times F. It also means that the volume should be equivalent to A plus square root of A times A plus A. All I've done is I've substituted capital A for lowercase a because the two bases are equal. Well, hey, look at this. This term becomes A plus A plus A, also known as 3A. This means that if I take the area and I multiply it by the height, I would get the volume if I assume it's a cylinder. If I take this mysterious constant, multiply it by the height, and multiply it by 3 times the area, I would get the volume if I assumed it was a frustum whose bases happen to be equal to each other. These two volumes should be the same, because I'm looking at the same figure. Either I'm treating it as a cylinder or I'm treating it as a frustum with 2 equal bases. So that means that AF should equal 3CAF. I can divide both sides by this AF term. Anything divided by itself is 1, and I'm left with 3C. I'm trying to solve for the C. I divide both sides by 3, and I get that 1/3 equals my constant. So because the volume of a cylinder should be the same as the volume of a frustum whose bases are equal, and because the formula for the volume of a frustum can be written this way, this constant has to be 1/3. And one of the nice things about this is that it does make an intuitive kind of sense. The way that a triangle is 1/2 the rectangle that it sits inside, a cone is 1/3 the volume of the cylinder that it sits inside. Areas are a 2-dimensional concept. They are flat on a plane. And volumes are a 3-dimensional concept. They come out of the plane and exist in 3-dimensional space. If we have a triangle, it is 1/2 of its 2-dimensional rectangle. If we have a cone, it is 1/3 the volume of its 3-dimensional shape. And so this is an explanation for where does the formula for the volume of a cone come from without using any kind of calculus or using any advanced limits or algebra. When you guys take calculus in the future, you will derive formulas for how we actually come up with defining a cone, which then also simplify to the same case. But it's always nice that in mathematics, these truths are universal. No matter what method you use, as long as it's applying math correctly and validly, you should arrive at the same result. Once again, thank you to Michael Hirschhorn from the University of New South Wales for publishing this methodology. And I hope this brings a lot of good insight and makes these formulas just a little bit easier for you guys to remember.